Could Earth ever become like Mars? Cold, thin atmosphered, and lifeless? Welcome to Infinite Cosmos. Today we'll cut through the headlines and follow the physics and observations so you can see why the answer is no on any human timescale. And what lessons Mars gives us about planetary fragility. Mars preserves clear evidence it was once warmer and wetter. Valley networks, deltas, and clay minerals that form in the presence of water. Those features imply a thicker ancient atmosphere and surface liquid water for extended periods. Over billions of years, that atmosphere thinned and the surface cooled. Multiple processes contributed, and the combination is what matters. Atmospheric loss works in several ways. Thermal escape removes the lightest gases when particles in the upper atmosphere reach escape velocity. Large impacts can blast atmosphere into space. Chemical sequestration locks gases into rocks, ices, or minerals. Crucially for Mars, non-thermal processes, sputtering and ion pickup, driven by the solar wind, have been major drivers. Energetic solar particles collide with upper atmosphere atoms, knocking them into space or ionizing them so the solar wind carries them away. Spacecraft measurements show ion escape continues today and spikes during solar storms, so the process is ongoing. Why was Mars vulnerable? 3 factors: loss of a global dynamo, lower gravity, and lack of long-term geochemical buffering. Early in its history, Mars's core stopped producing a sustained global magnetic field, so the planet lacked a magnetosphere to deflect the solar wind. Mars's gravity is only about 38% of Earth's, making escape easier. And without sustained plate tectonics and large oceans, Mars lost the long-term carbon cycling that helps stabilize an atmosphere. Over billions of years, even slow escape rates add up to dramatic thinning. Earth is different in 4 protective ways. First, a global magnetosphere generated by a convecting liquid core deflects charged solar particles and greatly reduces non-thermal escape. Second, stronger gravity suppresses thermal escape of heavier gases. Third, vast oceans and active plate tectonics recycle carbon and buffer climate through weathering and subduction. Fourth, biological processes have altered atmospheric composition in ways that stabilize surface conditions. Together, these systems make atmospheric loss to space negligible on human timescales. Human activity is changing Earth's climate by increasing greenhouse gases, which drives warming, sea level rise, and ecosystem stress. Those are urgent, solvable problems, but they are not the same as stripping the atmosphere into space. Changing composition and energy balance is very different from ejecting atmospheric mass. To reduce Earth's surface pressure to Mars-like levels would require catastrophic impacts or disabling the geodynamo. Scenarios beyond realistic human capability. There are other extreme fates to consider, but they differ in kind. A runaway greenhouse, the likely fate of Venus, would make Earth far hotter and inhospitable. Not thin and cold like Mars. On very long timescales, hundreds of millions to billions of years, the sun will brighten and alter Earth's habitability. But that is stellar evolution, not atmospheric sputtering. Terraforming thought experiments highlight scale and retention. Raising Mars's pressure to comfortable levels needs gigatons of gas and a way to keep it. Without a magnetic shield, any added atmosphere will leak over geological time. So both supply and retention are required. The reverse, deliberately turning Earth into Mars, would require removing most of our atmosphere or disabling our magnetic shield, which is neither practical nor desirable. The practical takeaway is simple. Earth will not naturally become like Mars on any human timescale. Mars's history is a warning that atmospheres can be lost when protective systems fail. But Earth's gravity, magnetosphere, oceans, and geology make a Mars-like fate extremely unlikely. The real immediate threats are climate change, biodiversity loss, and pollution. Problems we can address now through emissions reductions, conservation, and sustainable policy. If you want a tighter voiceover script or a teleprompter version for recording, I'll prepare it for Infinite Cosmos. Subscribe for more planetary deep dives and tell me in the comments which part you want next. Atmospheric escape physics, isotope evidence, or terraforming math.